Imagine you're training a model to recognize handwritten digits, say the number 3 versus 5, using only unlabeled data. You use contrastive learning. You generate two augmented versions of the same image, push them close together in representation space, and push other images apart. This works well if the test data looks like the training data. But here's the catch. In real-world applications, like medical imaging, autonomous driving, or industrial inspection, the data at test time often comes from a different distribution than what you trained on. Maybe the camera is different, the lighting changed, or the hospital uses a new scanner. This is called covariate shift, and it can wreck your model's performance. Now, what if you don't have labeled data from all domains? What if, in fact, most of your data is unlabeled? That's a common problem in practice. Labeling is expensive, time-consuming, and sometimes even impossible. So how do we build models that generalize not just to similar data, but to unseen domains, especially when we have sparse labels? That's exactly the challenge we tackle in this work, improving domain generalization in contrastive learning through adaptive temperature control. Let's dive into the core idea. The problem, contrastive learning breaks down under domain shift. Standard contrastive learning relies on the assumption that augmentations during training simulate the kinds of variations we'll see at test time. But when that assumption fails, say the test data has a different color distribution or a new sensor introduces noise, performance drops sharply. Why? Because the model learns to distinguish samples based on domain-specific features, like color, lighting, or scanner artifacts, rather than the invariant features we care about, like the shape of the digit. So we ask, how can we train a model to ignore domain-specific cues and focus only on the true task-relevant signals? Here's the twist. We do have domain labels during pre-training, but we're not using them to classify domains. Instead, we use them to intelligently adjust the contrastive loss, specifically the temperature parameter. You might recall that in info and CE loss, the temperature parameter controls how much penalty we assign to negative samples. A smaller temperature increases the penalty on hard negatives, samples that are similar to the anchor but not the same. That's useful because it pushes the model to be more discriminative. But what if we could make that penalty adaptive, not just based on similarity, but also on domain similarity? That's the core idea of our method, adaptive temperature control. We train a lightweight domain discriminator on top of the current embedding space. This network estimates the probability that any given sample belongs to each domain. Then, for each negative pair, anchor and its negative, we compute the probability they come from the same domain. We call this WH. Now here's the key. We use WH to dynamically adjust the temperature for that negative pair. \tauh equals \max lift. \tau alpha plus \tau beta lift. \frac1nd WH right. \tau min right. So if two samples are likely from the same domain, high WH, the temperature \tauh becomes smaller, which means a larger penalty is applied. This forces the model to push apart embeddings from the same domain, encouraging it to learn features that are invariant across domains. But here's the beautiful part. This adjustment is adaptive. As pre-training progresses, the domain discriminator gets worse at distinguishing domains, because the model is learning to suppress domain-specific information. So WH approaches \frac1nd and \tauh converges back to the baseline temperature \tau alpha. In other words, we start by punishing domain-similar negatives hard and gradually relax that punishment as the model becomes more domain invariant. This mimics a natural learning process. Early on, the model is confused by domain differences, so we help it disentangle them. Later, when domain information is no longer useful, we let the standard contrastive loss take over. Two variants, weighting by anchor or by pair. We explore two ways to compute WH. Domain-weighted negatives. We treat the anchor's domain as known and use a soft label for the negative. So we compute WH equals P, DJ equals DI, ZJ. Domain-weighted pairs. We use soft labels for both anchor and negative. So WH equals P, DI equals DJ, ZI, ZJ, which captures the probability they share a domain. We find both variants work well, but domain-weighted pairs tends to perform slightly better, especially under strong domain shifts. The experiment, a synthetic but insightful dataset. To test this rigorously, we created a variant of MNIST where digits are colored, red, blue, purple, green, each corresponding to a different domain. The digit color is drawn from a Gaussian distribution around a domain-specific mean, with variance \sigma. So for example, red digits are mostly red, but with some variation. As \sigma increases, domains overlap more, making generalization harder. We train on two domains, red and blue, validate on a third, purple, and test on a fourth, green, a domain never seen during training. We compare to several baselines. Standard contrastive learning. Same domain negatives. Contrastive learning with MMD penalty. DANN, domain adversarial training. And an oracle method, standard contrastive learning with color jittering, something we'd never have in practice. The results, outperforming the state of the art. Here's what we found. On out-of-distribution accuracy, our main goal, our method outperforms all baselines, including the oracle. On in-distribution accuracy, our model is still the best, even though it's been trained to ignore domain cues. The domain classifier trained on our embeddings shows very low accuracy, meaning the representations are highly domain invariant. Most importantly, our method maintains strong in-distribution performance while improving OOD robustness, a rare combination. And here's a deeper insight. As color variance $\sigma increases, our method becomes more robust. Why? Because with higher variance, domain information becomes noisier and harder to encode. Our method is better at ignoring that noise, freeing up capacity to learn the true digit structure. This suggests adaptive temperature control is especially powerful when domain shifts are subtle or complex, exactly the kind of real-world scenarios we care about. Why this works, a gradient perspective. In standard contrastive learning, the gradient update for a negative sample depends on its similarity to the anchor. But the magnitude of that gradient is scaled by \frac1 \tau. Now in our method, \tau is not fixed. It's lower for pairs that are likely from the same domain. So the gradient for those hard negatives is amplified, meaning the model is pushed even harder to separate them. This creates a self-reinforcing loop. The more domain information is encoded, the stronger the penalty, the faster it gets removed. And crucially, this is done without competing with the main contrastive loss. The domain discriminator is trained separately, and we don't backpropagate through it to the encoder. So no conflict in objectives, just a clean auxiliary signal. Final thoughts, a simple idea, powerful impact. This work shows that a small, elegant modification to the contrastive loss, adaptive temperature based on domain similarity, can dramatically improve robustness to distribution shift. It's not about adding complex architectures or adversarial training. It's about using available domain labels wisely, not to classify, but to guide the learning dynamics. And because it's modular, it can be plugged into any contrastive framework, SimCLR, MoCo, SupCon, making it broadly applicable. Looking ahead, future work could explore using more sophisticated domain discriminators, batch-level discriminators to capture local shifts, alternative ways to compute $, or applying this to real-world datasets like medical imaging or satellite data. But for now, the message is clear. When you have domain labels during pre-training, don't just ignore them. Use them to sharpen your model's focus on what truly matters. Because in the real world, the data will shift. But with the right tools, your model can stay ahead. Thanks for watching. If you found this helpful, please like, subscribe, and share with anyone working on self-supervised learning or domain generalization. Stay curious, stay critical, and keep pushing the boundaries of what models can learn from unlabeled data.